Swayam Prabha. Digital India. Educated India.
So, this is going to be our actual first organic topic, I believe, right? So, before all, it's an inorganic physical theory aspect, and of course, yesterday Professor Biraya covered a green chemistry aspect, which is again probably would come very close to this. I saw in the pool which I sent, this good number of an organic chemistry interest was there, right? That's interesting. So, what do you guys like in organic? So, name reactions, reagents, or you are able to derive the product easily if you are given an option. So, that's what makes you feel more comfortable with organic. Other words, what do you like in it? Mechanism, very nice. Naming reactions, you are able to remember it. Okay. Sorry, what? That's awesome. Okay, like there is some stereochemistry involved in what we are going to discuss today, but not in hardcore stereochemistry. Of course, the reaction which we are going to see is more often stereospecific transformations. Okay, so generally, if you want to divide the reactions, okay, general problem with an organic chemistry, if somebody who does not like would say, probably there are too many reactions or too many reagents. How do I connect these dots? Right, probably if we can segregate or classify it in a better way or understand the kind of species involved, probably we can narrow down our thoughts, or in other words, be more focused in what kind of reaction one could expect, right? In general, if you want to win in a larger basket, if you are thinking with respect to kind of species involved, means the reactive intermediate which are involved, we can classify them in three different big baskets. Okay, so give me one example of one of the reaction, any one reaction in organic transformation. Any one organic reaction? Rosenman reaction. Okay, anything else? What is Rosenman reaction? Acyl chlorotone aldehyde. Okay, that's metal involved. So, we do not want a metal of that type, like palladium kind of things involved. But very simple reaction, very simple reactions. Oh, that's a rearrangement. Okay, fine. That's in basic to see, right? Hydrations and all you talk about bromination. Very simplest reaction, displacement reactions, for example. All this would involve an electrophile and a nucleophile. Okay, so leaving the reaction what she said about Rosenman, where the metal is involved, but the chemistry itself altogether very different, right? Or with respect to a rearrangement transformation, which are very interesting, which are very different as well. Of course, there also, if you look at it, there's an electrophile nucleophile reaction would potentially occur. But these reactions where you have clear electrophiles and clear nucleophiles, and they tend to react, those reactions can be generally called as polar reactions. Okay, so that's a first class, right? The first reactions you talk about is polar reactions. So, in this case, you would have an electrophile reacting with a nucleophile. So, that means in any given reaction when you are thinking about, you first aim to see where are the reactive sites, where there is an error. So, if you have to form a bond, right, you need an interaction resulting to a bonding, plus you also need two electrons in then bonding arbor so that you define a bonding eventually, right. So, in this case, to form a product, the new bond which is formed, which has a two electron in a sigma bond. If you consider this sigma bond, that sigma bond will have electron that comes from only a nucleophile. So, electrophile at an empty orbital, which is react with a nucleophile to give you a new bond where the sigma bond has a 2 electron that came from a nucleophile. So this, if you understand, the most of the reaction which you see it in an organic chemistry can be a salt. Means looking at what are the property of the species what you are using, how it can potentially react, and where the reaction sites in the coupling partner, the reacting partner, and how to derive the reaction. Right? So if you look at the bromination, what he means, right? So bromination means you are going to have a kind of, let's say, an alkene reaction with an bromine. So in this, which is electrophile and which is nucleophile? Bromine is nucleophile. Br minus is a nucleophile. Bromine Br2 as a Br2, it is an electrophile. Your alkene is a nucleophile. So this would react like a nucleophile, and this would react as like an electrophile, would give you a species which is an bromonium ion we talk about, right? And then you will have a counter ion Br minus, which can potentially open up either from here or from here. It depends on the R substitution. Am I right? You will have a ratio of the product, depends, because here you don't need to worry about, because both the atom you are adding a bromine. So you are adding an identical species. So you are not going to differentiate, you need not be worried which side it opens up. So like this, if you are able to understand the reactivity of the species, it is rather easy to derive the product what potentially can form. This is one such a class of reaction. The second, looking at the very similar concept, what could be the second reaction? The second big basket when you talk about. In the first case, only the nucleophile brings an electron to form a bond. What could be the next one? Where the both atom which come in to form a bond can bring its own electron and share, which is like a radical reactions, right? The second class of reaction one could think of is like a radical reactions. In a radical reactions, you have two species obviously reacting, right? And both carries an electron, which can eventually result to a new bond formation. And in this bond formation, unlike here, you have the electron which is in a sigma bond, it came from both the partners. So those are like a radical reactions. Of course, radical reactions has its own pros and cons. There are advantages, there are disadvantages, which I mean. So disadvantages, it can undergo kind of propagation reaction. There are multiple new species can form. The control could be relatively difficult, but there are other possibilities where the very unique kind of transformations are not possible through an electrophile nucleophile can also be achieved, right? So that way, the radical creation also has a lot of upper hand, and it's interesting as well. So this is second class. These are something which I am not going to talk to you guys today. The third class is what? Initially, it came from one coupling partner, there it is shared. What could be the third type? So third type is then, don't talk about an electrophile nucleophile or radical kind of things, but then we classify as some pericyclic transformations, right? Which I asked you guys yesterday. What is pericyclic reactions? A third class. You are not going to see an electrophile nucleophile in this. You may not be seeing of course, you might see a zwitterions and other things, depends on the kind of reaction what you are thinking. Zwitterions, you know, right? What is zwitterion? Okay, what is elide? Okay, so if they are in the next atoms, the neighbor atom, they are called them halides. So all halides are deuterions, but not all deuterions are halides. Okay. So a pericyclic reaction, what you understand by this pericyclic reaction, the term sorry, pa? It is a single step transformation, which means what does that mean? A single step transformation means what does that conveys to you? Oh, that is an important point, right? So this is an concerted process. All the pericyclic reaction what we talk about are in general a concerted process. Concerted process itself defines is that you do not have an intermediate formation, right? The first thing is it's a concerted process. Which means you do not have an no intermediate formation, right? In a typical reaction, when you look at it, for example, an SN1 type reaction, for example, when you look at it, if you remember a reaction profile, if you look at with respect to potential energy versus reaction coordinates when you see, right? So you go from a starting material to product, you would potentially have an intermediate formation and then a product formation. So this species what you are looking at is an intermediate. Correct? No. So what about this? This is a transition state. So in a pericyclic reaction, what we talk about, you do not have this possibly forming. Okay, this is a considered process without going through an intermediate, but there is a reorganization of an electrons in a molecule, creating a new bond through a cyclic transition state. Okay, which means this is for a typical reaction. In a pericyclic reaction, you would potentially have either these two could be an equal, depends on the reaction. It could be little different with respect to the relative energy what you are talking about. So you would have a transition state. In mostly these transition states are cyclic in nature, because if you look at most of this reaction, you would have the pi bonds in a molecule kind of rearranges itself through a cyclic transition state, not forming a specific intermediate and resulting to a product. Okay, those kind of reaction what we classify as a pericyclic transformations. Okay, so now tell me what are the type of pericyclic reaction which you know? Okay, cycloaddition, then a sigmatropic, then cycloaddition, sigmatropic. Very good. What is next? What are the other pericyclic reactions which you are aware of? Disorder is a part of an cycloaddition reaction. In reaction, but that could come as what is called as a group transfer reactions. Right? In general, in reaction is kind of a group transfer reactions. What else? Have you heard of an electrocyclic reaction? Electrocyclic reactions? No? It's good that I picked the right topic. Okay, so what is the last one? There's one more, which is in heliotropic. A heliotropic transformation, a reaction or rearrangement when you talk about. So these are the 5 reactions generally you discuss in pericyclic transformations. There are other reactions which may not go through an intermediate, but it has its own way of classification. So this 5 reaction what you are going to see is in a pericyclic reaction. And today Luckily, I chose the right topic, which what we are going to see is in electrocyclic reaction. And one more interesting aspect in the pericyclic reaction of this type are they are reversible transformations. So all these reactions are reversible transformation. You can go from a left to right. You can also come from a right to left. Both are potentially possible. When you particular condition, you might get into ratios of mixtures based on their stability, or of course, when you are asked a question, you don't think about that aspect. You'd like to see if what is given, what is the condition, and how you can arrive at this particular transformation. Okay. So, but all these reactions, because there is a rearrangement in a pi cloud, right? The cyclic transient, what we talked about, these reactions are generally stereospecific in nature. It's very good. Under a specific condition, there are three parameters which you consider in this particular cases. That means the outcome of the stereospecificity in the reactions depends on three things. One is substrate, a geometry of a substrate, which means E, because I mentioned an alkenes which are reacting, right? Whether you are starting with an E alkene or a Z alkene, where this terminal vertex reacts, that's one important point which determines your outcome, the stereospecificity, what is exactly going to come. And second is number of electrons involved in the reaction. Because I said the pi systems, so all the pi system would have an electron and number of electrons. In this, what we kind of simplified towards the end, like an aromaticity, we classify them as either a 4n or 4n plus 2 type. Okay, so it becomes very easy to count because it's all pi system, then it's easy to count as either a 4n or 4n plus 2. This is second. And third, which you would control, is a condition, which means whether you are performing a reaction under thermal condition, which we generally represent as either a thermal, a heat, or delta, right? So these are the way you represent it, either in the form of a delta, or in the form of saying heat, or in the form of saying a thermal conditions. And other one is either a photochemical or IGNOU, either one of them. Okay, so these three, even one changes, you would have an outcome different. Okay, so this is common for all the 5 reactions what I talked about. It's not for the reaction what we are going to see today, but then for all the pericyclic type reactions what I mentioned, these phenomena are constant. These 3 are the one which determines an outcome of in any given reaction. Okay, as I said, you change one of them, your outcome will be very different. Let's move on with reactions. Okay, so now let's look at a pericyclic reaction. One of the class, as I said, an electrocyclic reaction. Electrocyclic reaction, in general, it is an unimolecular transformation. Okay, the conjugated polyenes, it could be a conjugated polyene. This is a 1,3-butadiene, or you can also think about an higher analog. Hexatriene. Okay, either a butadiene or 1,3,5-hexatriene, they are conjugated polyenes. The conjugated polyene can undergo a reaction either in presence of a heat or in presence of a light to give us a new product, which is in this case, if it is a butadiene, you get a product which is an cyclobutene as a product. Okay, so how does, if you wanted to remember to how we write this reaction, it's easy to push an arrows, because that's the first thing you'll have to learn in an organic chemistry, to know how to push an arrows. Okay, always push an arrow from an electron rich position to an electron, because it's a flow what you are looking at, right? So that's your direction. But here You don't need to worry about. I can do either clockwise or an anti-clockwise. It does not matter to me here. So I can probably show it this way, such that, which means I'm breaking up both the double bonds, creating a bond between, if I number this, create a bond between 1, 2, 3 and 4 if you say, exactly. So it is 1, 2, 3 and 4. So I have created a bond between and 1 and 4 by breaking a bond between 1 and 2 and 3 and 4. In the process, the way I moved has and one more bond now generated between 2 and 3. So this is how you push an arrow and draw your product. This is a for as I said, it's an electrocyclic reaction is an unimolecular transformation of a conjugated polyenes and undergoing an cyclization. So this we also can say as an electrocyclic ring closure. The forward reaction what we talked about is an electrocyclic ring closure. Okay, so as I said, if you have in any system having this kind of framework, which means a cyclobutene, if you have it in your molecule, then it can open up and go to exactly as I told you, these reactions are reversible. So I can go back to an butadiene. So that is called as an electrocyclic ring opening. Okay, the reverse reaction is called as an electrocyclic ring opening. This is for an butadienes. The same you can also do it for an hexatrienes or even in higher analog. We will see today possibly even higher analog what are possible. So if you wanted to see that way, once again you push an arrow such that, as I told you, I am doing here in an anti-clockwise, you can also do it in clockwise, does not matter. This arrow pushing kind of helps you to convert your starting material to a product. How do you arrive at the product from a starting material? This kind of arrow pushing would help. Now once again, if you want to number, it's 1, 2, 3, 4, 5 and 6. And the product would be cyclohexadiene is a product. Okay, once again if I number, it's 1, 2, 3, 4, 5, 6 here, and the new bond which is formed, the new sigma bond what is formed is between 1 and 6. And then the way I pushed the double bonds, all the double bonds are broken, they are not at the same position. Now it has moved to 2 and 3 and 4 and 5, and then the 1 sigma bond is formed. So now knowing this reaction, if you want to even more generalize this, as I said, it is an unimolecular transformation of and conjugated by alkene, polyenes for example, right? Conjugated polyenes. Remember, that's the first thing. In the process, what happens if it is looking at a ring closure transformation, you will have the product will have one sigma bond and an n-1 double bonds. If I start from two double bonds like a butadiene, what I mean, the product will have 1 sigma bond and this is 2 double bonds. So the n-2, n is 2, 2 minus 1 is a 1 double bond what you get. A hexatriene, it will be 1 sigma bond and there you have a 2 double bonds. So here for butadiene we have no problem because this is a sigma bond, right? So I always can have this option. So how do we classify these two compounds? Yeah, cis and trans, but it is not a normal cis and trans, right? Sorry, Pa. You call them as an S cis, and S refers to a single bond. Across the single bond, right? Across this single bond, this is cis. They are placing an a same direction. Okay, across this single bond here, they are facing a trans. In a butadiene, for some reason, it could be steric, it could be electronic, for some reason, if your diene is placed in an S trans form, those molecules will not undergo electrocyclic ring closure. The reason? That both the terminals cannot interact such that to give you a product. Is it clear? Right? If you take a butadiene, you have to have an S-cis form, then only the terminal carbons can interact to form the product like what I mentioned here. If it is in a S-trans form, they will be far away, they can never interact and give you a product. Which means, for some reason, if you have a reaction that results you to, or substrate, I'm sorry, the substrate which has an exactly S-trans form, you would potentially not have a reaction occurring. For example, say it's a conformationally frozen. This is a butadiene, it's an S-trans form, right? You can have even open structure, 2,3 distributyl butadiene also stays in S-trans form. These molecules would not undergo electrocyclic ring closure. The molecule should have even at least 1 or 2% of an S would be possible. Then only you can have a reaction happen. Otherwise, there is no possibility. All right. That is with respect to butadiene. But now we are not only going to worry about butadiene. We have a lot more derivatives. You can have a 6 carbon, you can have 8 carbon, you can have 10 carbon, you can have an n number of the polyenes what we talked about, right? The conjugated polyene. Here the limitation what you are looking at is the terminal can be cis or trans. We don't need to worry about it. So if I put a double substitution here, that could be trans or cis. We don't need to worry because that still can interact. The terminal can interact. But what the limitation is, the internal double bonds has to be always cis. Irrespective of n number of intervening double bonds in your molecule, right? A hexatriene has compared to those two terminal one, you have an internal, there is one double bond. That has to be a cis double bond. If you go to an octatetraene, for example, right? An octatetraene has now 2 double bonds which are internal and both has to be cis. If it is not cis, forget about it. There won't be any reaction at the terminal, but there could be some other reactions. For considering that if I have a system which is this, the trans, these two may not interact, but however I can interact between these two. So this way you need to think about what are the possibilities also one can think, get out of this. Alright. So this is about an electrocyclic reaction. I have not shown you any substitutions over here. I have not placed any substitution, but I talked about a stereospecificity with respect to these transformations. Let's see what happens when you have substitution. Alright. So let's simply take butadiene and put a substitution with this methyl group. Okay. And I am going to now, because the stereochemistry is trans in both the olefin what we looked at, right? I am going to kind of one case shine a light, other case I heat. Okay. What would be the outcome? So my substrate is same, right? The number of electrons which is involved in this, it's same, because how many electrons are involved in this? 4 electrons, right? 4 pi electrons are involved in it. The geometry of an olefin is same. Remember the 3 conditions I told you. So electron is same, geometry of alkene is same, but what I am now changing is a condition we are changing, whether thermal or photochemical. Okay. So thermal would give you, do you know what is the, okay, product what would expect here? So you would get, in this case, a trans product. I'll explain you why it is called. Okay. When you heat a 4N system with this particular alkene, you would end up getting a trans product as a major product. And if you shine a light, the product will be cis. This is what I meant. Okay. Now let's do the same small change in this particular system. Because this condition changed, now we'll change, and one of the olefin geometry changed. Now the number of electrons same, right? 4n electrons, but the geometry of the alkene changed. If I heat this, that means substrate same, I'm looking at heat, but the geometry is different. Now I get a cis product. But if I do a photochemical condition, I get a trans product. In the same way, now we looked at a geometry, we looked at a condition. Let's look at an electrons, number of electrons. For example, I have once again, if you look at it, this is also trans. The reacting terminal alkenes are trans in relation, both are trans. Now the number of electron involved, here it was a 4n, rightly you said, right? In all these cases it's a 4n. But here it is, there are 6 electrons. This will be classified as n and 4n plus 2. Okay, so n is 1. So in this case, when you heat, it is an 4n plus 2 as we said, or when you shine a light, you are going to have a product. I am not drawing here an arrow expecting that you will be able to push the arrow and get the product. Now I am worried about a stereochemistry of it. So here we said trans, but here you get under thermal condition a cis product. And other case we get a trans product. A same and applies to the system if you go from, if you change one of the stereochemistry of an alkene, here it is E and here it is Z, you have both an E here, right? Once again, you would have a very different product formation here. Under thermal, which was cis, now it becomes a trans. Under photochemical condition also, once again it would change to give us a cis product. That is convince you, right? The 3 aspects which kind of determines your outcome to start with, which we discussed in the beginning, right? This is an example to prove that those 3 aspects really does the job. One, the first one is, okay, geometry of an alkene and E or Z olefin at the terminal. Most of the case we are worried about the terminal alkene because internal one does not much change. It doesn't give any stereochemistry because that becomes still it stays as an sp2 carbons. The internal carbon would remain stay as an sp2 carbon. So no stereochemistry coming into picture. So we need not worry about. So we will worry about only the terminal alkene which are coming closer to form a new sigma bond. So that ERZ is a first thing. The second, a number of electron which is involved. So you generally we classify as either a 4n or 4n plus 2. Then the third one, a condition, either a thermal or photochemical, you have a different observation. Now, this is an observation. This information is given. Now, how do I rationalize or how do I kind of predict? If at all you have to predict, for example, how do I do this? That's the next step. So that requires an understanding of how the reaction occurs, the electrocyclic reaction, how the ring closure, how the ring opening occurs. That we need to kind of first understand, then we'll have a clarity about how we go further. Right. So now I told you the pi bonds, in a conjugated polyene, the pi bonds are reorienting such that the new sigma bond is formed. That means the terminal carbon, the pi bonds are kind of interacting. So what are the way it can interact? Let's look at, this comes under, there are two possibilities. One is a disrotatory, other is a conrotatory. So let's take a very simple example. We are not going to see an complete molecular orbital system, but we are going to take only the terminal to explain what is conrotatory, what is disrotatory. Okay. So let's take only the terminal atoms which has lobes which are connected. Right. So now consider I have such an orientation. Okay. If you know that if in a molecular orbital the interacting bonds, like in the orbital, the way it interacts, the sign of a coefficient has to be the same. Then only you will have the bonding. If it's opposite, means you will have a node, isn't it? Which means if the terminal lobes are like this, if it has to form a bond, you consider this is plus and this is plus, these two have to interact to form a bond. If these two interacts, then there will be a node, so there won't be any bonding. Do you agree with me? So which means if I have to rotate this to create a bond, so consider that this is an axis what you are looking at. So I have to rotate in the axis, what I am doing in a clockwise rotation. So the whole thing I am rotating this way, right? So same way, now if this comes here to interact and the bottom lobe has to come up to interact. So that also, once again, if you see in this axis what you are looking at, once again what you are supposed to do, you are supposed to bring this up. So that means it has to be clockwise. So in this again clockwise. So what would be your transition state in this particular case is you will have something like that, where eventually you are going to have an interaction this way, which would create a bonding. Okay. So this kind of mode of rotation, that means where both end rotates either in clockwise direction or in anti-clockwise direction. That means if I do an anti-clockwise, I will have if consider these two are plus, that means these two are minus, the minus lobes would can still interact and give you a bonding. Do you agree? So that means if both the ends rotates in the same direction, it could be both clockwise or both anti-clockwise, they are called as a conrotatory. Okay. In a simpler form, what we say is a con. So, which means if this has to happen, your molecular orbital which you are looking at has to have a sigma antisymmetry. Because there is some molecular orbital which we are going to see in the coming 10 minutes after that. So, we will see that if the molecular orbital which you are considering to do this particular one, if this has a sigma plane antisymmetric, that means there is no sigma plane in this particular case, then those molecular orbital can undergo counter-rotatory given a bonding. Now, the same system we will take. If again I am connecting these two, let's maintain the same asymmetry with respect to molecular orbital. Okay. Now, as we did before, let's do on one side a clockwise. That means n clockwise, and then an other side we do an anti-clockwise. Right? We do an anti-clockwise. Right? This is what I meant. That if this happens, you would potentially have the transition state would look like this, where there is a node. So, this interaction cannot cannot lead to an bond because there is a node. Do you agree? So, this is not a favored, or when you say it is favored, and this will be a favored one. Do you agree? So, this we described as an con rotatory, a con in a simpler form. This kind of way where at one end you do a clockwise and other end you do an anti-clockwise, you classify them as a disrotatory. In simpler form, we call them as a dis. So, if you kind of forget, I used to always tell my student that if it is D refers to different. If you remember that, you will be able to say that both ends they are not the same way of rotation. You get my point? It is not a chemistry, it is just only to remember. Make sense? Right? So, this case once again it is sigma and antisymmetric. So, the molecular orbital which you are going to look at it, if it has a sigma and antisymmetry, then the mode of reaction would be a con-rotated given and bond. The disrotated does not form a bond. Okay. Now, let us take another example. Where you have a molecular orbital has a sigma symmetric in nature, which means you have so this is a sigma symmetric. Do you agree? Now, let us perform the same two operations. One is con-rotatory, otherwise is disrotatory. So, which means I am going to do now a con-rotatory over here, and this is in a clockwise. The same way I am not changing this, and this in an again a clockwise, you are right. right? So this goes this way and this comes this way, and this would give you so this interaction would give you a node, right? So there won't be any bonding formation. So if it is a con, then this is disfavored. However, if you take a same system, now once again I chosen a sigma asymmetric system. Then I have now rotate one in these two axes, one in a clockwise, other in an anti-clockwise. This way it goes, and then here this way it comes. I would potentially have a transition state which is like this. So now this interaction can lead to a bonding, and this will be a forward. So this is to basics to understand. So how the reaction occurs. So this electrocyclic ring closure can potentially occur through two modes of cyclization defined by how the terminal carbons are interacting. So which direction, which lobes are basically interacting, which side of the lobes are, because if you look at a polyene, your sigma bond is in plane what you are looking at. So you have pi bonds above and below the clouds. So the which side it's going to react. In a con rotation, you will have in one carbon you will have a top and other carbon will have a bottom, or vice versa. In a disrotation, a same side of a lobes would react or interact. I would not say react and interact because it's rotation. It's an interaction, right? So these two would interact, or the bottom, both the bottom or both the top would interact and give a product. Okay, so this an analysis of in general pericyclic reaction can be done by three different ways. Okay, so the one of the first one which was developed by Professor Woodward and then Hoffman is what is called as a correlation method. What you call it a symmetric correlation method. Have you heard of this? A symmetric correlation method. That's the first one. So one can analyze this one by what is called a symmetry correlation method. This was developed by Professor Woodward and then Hoffman, which is very involved one. I have to draw all the molecular weight of molecular orbital of my starting material. Also, I have to draw all the molecular weight of my product which are involved in the reaction, not all of them, only the one which are involved in the reaction. Then I look at the symmetry and then start correlating, and then I tell about whether the system is allowed or not allowed. This is a very involved one. And the second one is a transition state, an aromaticity method, which only uses the lowest energy molecular orbital, which is a psi 1 of a system. Also, it is called as a perturbed molecular orbital method. Okay, this was done by Zimmerman and the other person who kind of independently developed this. Okay, this is an kind of involves what is called as an Huckel's aromaticity and Mobius aromaticity with respect to the presence of node. They use and how the similar kind of interaction, but however they use and psi 1 of your molecular orbital to derive at this particular one. The third one is what is called as an frontier. Frontier molecular orbital method, which is done by Fugi. Of course, initially was kind of introduced by once again Woodward and then Huffman, and eventually by Fugge, because who described an FMO. What are frontier molecular orbitals? Which one you classify with the frontier molecular orbitals? A HOMO and LUMO, right? On any system, you talk about an HOMO and a LUMO. What is HOMO and what is LUMO? So, highest occupied molecular orbital. Highest refers to what is nothing to do with an excited ground state. In a molecular orbital, when we arrange it, we will see that in a minute. Highest refers to what in HOMO? That's a question. It's highest refers to highest in energy of a field orbitals. Okay, highest occupied molecular orbital. Occupied refers to, that means you don't worry about an unoccupied one, but however you worry about an in an occupied which has an highest in energy. Right? You go from an psi 1 to an psi n when you write it, the lowest will be, if you refer to a 0 and then it keeps going up, the one which has a filled, it could be partially filled also. No need to worry about it. We only refer to a filled one. It's not, it doesn't say a completely filled situation. You need not have 2 electrons. Even 1 electron, you still call them as an occupied one. Okay, so that is in today's scenario, they also call it as a SOMO, a singly occupied molecular orbital. There are other terminologies have come. Okay, but for our discussion, we restrict this as an HOMO. Whether 1 electron or 2 electron does not matter to us, as long as it is occupied and higher in energy, you classify them as a HOMO. LUMO is exactly lowest and unoccupied molecular orbital, which refers to one among an unoccupied molecular, which is the lowest one. Because those are the one which potentially interacts. The HOMO is the one which is highest in energy, has an electron, can give an electron to the system to start the reaction, start an interaction. That's why you consider HOMO in one system. A LUMO is the one which is the lowest in energy, which is unoccupied, can accept an electron. That's the reason why you kind of consider a HOMO and LUMO. So, we are not going to see these two methods. However, we will probably look at frontier molecular orbital methods to explain and derive it and final selection rule. Okay, we will see that quickly. Clean this, give me a minute. In an electrocyclic reaction, we said it's a conjugated polyenes which is reacting, but this is very specific. Only the pi systems are going to rearrange. The pi bonds are only rearranging the way I have shown. The sigma bond is in a pi orbital when you look at it. Sigma bond lies in a node. It's a node. If you look at a pi bond, the sigma bond versus a pi bond when you look at the sigma, the carbon-carbon sigma bond will be a place itself a node. Because a pi will have one node, which is this, pi star will have 2 nodes. Isn't it? Here, we are going to kind of forget the sigma plane itself, which is already node, we will not consider. We will only consider, we are going to derive only a pi molecular orbitals. Okay, remember the sigma plane itself is a node for your pi orbitals. Alright, so if you talk about an ethylene, so how do you draw it? So you have, consider that you have bring a 2 carbon. According to MO theory, it's a mathematical and addition subtraction way of deriving at your molecular orbital. So I'm going from an atomic orbital to an molecular orbital. So in this process, then orbitals are conserved, which means the number of orbital I start with, an atomic orbital which I start with, I'll have a same number of molecular orbitals, isn't it? And then what are the other rules which you remember? If you have an n number of an atomic orbital which you are interacting, if n is an even number, then an n by 2 will be a bonding and n by 2 will be an anti-bonding. Do you understand what I mean? Right? If you are starting with an n number of atomic orbitals to form a new molecule, for example, which involves all these parameters, then you will have an n by 2 will be, that means half of them, provided n is an even number, odd number can vary based on a carbocation or carbanion. But if it is an even number of carbons, then an n by 2 will be, and half of those n will be an bonding orbitals, will be having an electrons in it, and half of them will be an anti-bonding orbital which will not have an electron in it, right? And the other things are that the lowest in that will be having no node. What is node? No. A node is the place the probability of finding electron is 0. What is molecular orbital itself? Molecular definition itself, in a molecule, see in a normal sense of an orbital, when you talk about an atom, there you say the probability of finding electron in an atom which you classify as an orbital. In a molecular orbital, you talk about in a molecule, that's the only change, right? Atom to molecule you go. In a molecule, the probability of finding electron, where it is, that's you call it classified as a molecular orbital. If the probability of finding electron is 0 in a molecular orbital, that position you call them as a node. So if you think about making these two a carbon, right? Consider that two p orbitals are interacting, the two atoms are interacting. That means I'll have, when you say that orbitals are conserved, that means then go from 2 atomic orbital to 1 2 molecular orbital. So that interaction would be, when you have an addition, I can have a pi bond, or you can also say a pi or a psi 1, because I'm using psi 1 because when you go to higher order, it will be easier to put a psi 1, psi 2, or you can also say pi 1, pi 2 or pi star. In an ethylene it's easy, right? 2 carbon I take, 2 pi bond p orbital I take, I get a pi and then I get a pi star. Right? Either a pi star or you say it's an pi 1. The different book refers to one different vapor. Right? Does not matter. For us, we need to know which is HOMO and LUMO. So, which means here I would have, I took an 2 p orbital, both would have an 1 electron. That means I start with a 2 electron. So, where do I place based on Hund's rule? Because this is an energy, right? The potential energy what you are looking at is in this order, right? It will be increasing order this way. So, where do I place these electrons? The lowest energy one. So, this is this way. This is how it is placed. In this, which is HOMO? In this, there are only 2 orbitals. One is HOMO, other one is LUMO. There is no problem here. This is the only orbital which is occupied in an ethylene. This will be the HOMO, and this will be the LUMO. Now I am going to increase by, instead of 2, I am going to increase by 2 more, which is 4. Then I will have, how many molecular orbital I will have? 4 molecular orbital. So as I told you that the lowest will have a 0 node. The next energy level will have 1 node, because this is a node. So if you, that way if you look at it, if the way you want to arrange them in an order of energy, so going from lowest to highest, a lowest will have a 0 node, the next you will have a 1, the third one will have a 2, and that way when you go, an n molecular orbital will have an n minus 1 node. We will see that when you go to a 4, let us look at this. I am just drawing a linear form for our convenience, right? So that means I am going to create. So these 2 energies are not related, okay? I cannot draw all of them, placing in and perfect energy. So you will have this way a 4 molecular orbital generated. Then I look at 0 node, that means the phase, the sign of this orbital coefficient will be the same. The plus means plus for all of them. So 0 node, this will be a psi 1, And then the next one will have one node. The node has to be placed in a symmetry point. It's not like I cannot place it here. 3 on one side, 1 on one side. No, not placed in a perfect symmetry side. So then I'll have a one node with a which is like this, which is a side 2. When I go to the next one, I'll have 2 nodes, which has to be once again place because once again I cannot place alternatively. I have to place the overall symmetry in the molecule as we mentioned. It would be either sigma or n C2 symmetry. So that way, if we see, it has to be like this. The highest one supposed to have, in this case, there are 4 molecules. Obviously, it will have a 3 nodes, which will be like this. So we started with then 4 atomic orbitals, right? You have now 4 molecular orbital, and how many electrons should be there? 4 electron. So if I start filling once again, the first one will have 2, the second one will have 2, and third will be empty, and fourth will be empty. Am I correct? In this case, what is HOMO? Exactly. This is HOMO. Side 2 is HOMO. And side 3 and side 4, side 3 will be a LUMO. Very good. We can extrapolate this further to an hexatriene. Then from there, of course, you can keep going. We'll look at only those 2 cases, and then we can, I'm sure that we'll be able to extrapolate it further.
SwayamPrabha, Digital India, Educated India.